is most commonly known as the slenderness ratio. Okay, L over R is known as the slenderness ratio. Okay, so some of you might, okay, so what? Okay, or not so what? How do we get R? Okay, how do we get R? So we know that R is equal to square root I over A. We know that. So if we, so I post this on Avenue to Learn. Okay, so if you go to your weekly notes, let me show you, and because we need this diagram, and if you go to week number 1, you click week Thursday example, they're all here. Okay, so if you could, which you are all online now, I hope you all can download this. Okay, because we're going to use the images, so you won't be as confused or won't be confused. Okay, so we're going to look at this table now. Okay, we're going to look at this table. Right. So this is the table that you can find in your textbook. It's in page A19, and this is a I-beam cross section, and these are the type of beam that industry has. Okay, and over here is a table. Okay, so A means cross sectional area, D is flange, and one thing I want you all to now take note, like this part of the structure, okay, this part of the structure is known as a flange, and this part of the structure is known as the web. Okay, so get to know them now. Okay, what is a flange and what is a web? Now, why is that important? Because for the next column, it tells you what is a flange. Okay, so BF, this is the flange. Okay, width of the flange. TF, this is the thickness of the flange. Then you have web thickness. Okay, so this vertical part is known as the web. Then you have second moment of area. Okay, IXX about the x-axis, IYY about the y-axis. Then you can see RX over here. Okay, then you can have RY. So Rx is the radius of gyration about the x-axis. So we remember what you say, R is equal to square root I over A. So if we take the square root, so I is equal to 347. A, right, I is equal to 347 times 10 to the power 6. And then divide by your area, which is 18200, right? So when you use your calculator, 347 power 6 divided by 18200, square root of the whole thing is 138. By right is 138.1, but what you see over here, they round it off to what? 138. So that is your radius of gyration. So you can get your radius of gyration from this table. Okay, but the most important thing is this. Okay, the most important thing that I want to drive is this. Okay, before I go on, anyone, any question? I hope this is clear. Okay. Okay, I don't have any questions. So the most critical thing that we come out is this formula over here, where we have PCR is equal to pi squared E bracket L squared EI. Okay, this is your PCR, right? And then your critical load is pi squared E over L over R squared. Okay, so these two formula, right? These two formula are only valid or are valid when, number one, both end of the structures are what? Thin. Right? Both end of the structure are pins. And the second condition, okay, both end of the structures are pin. And the second condition is the structure is under centric axial compression loading. Okay, are we clear? Okay, so graphic or in terms of diagrams, if you sketch a diagram, what does it mean? Okay, so it means this. This is only true when the structure is loaded in this manner. Okay, both end pins and the load is coming down P. Okay, so P cannot go left or right. Okay, P must act exactly on the what? On the centroid. Okay, P must. So this is a very unique what? Unique condition. Okay, so let's look into an example. Now let's look into an example. Okay, let's look at an example. So the first example, we are given that the stress allowable is equal to 250 times 10 to the power 6 Pascal, right? And then we have a Young's modulus is equal to 200 times 10 to the power 9 Pascal. So we're going to determine the L over R ratio. Okay, let me later on tell you why, what is so critical about this L or not ratio, about this L over R ratio. So we know, right? We know that stress critical is equal to pi squared E over L over R squared. So now we would like to determine L over R. So it's equal to the square root of pi squared multiplied by the Young's modulus divided by stress critical. Okay, divided by our stress critical. So this stress allowable is also our stress critical for this case. Okay. So over here, we start putting in numbers. So we have pi squared multiplied by 200 times 10 to the power 9. And then we divide by 250 times 10 to the power 6. Okay. So this thing is equal to 200 power 9 times by pi squared divided by 250 power 6. Square root of the whole thing is 88.86. So what does this 88.86 mean? Okay, what does this 88.86 mean? Okay, so now I'm going to sketch a graph now. I'm going to sketch a graph now. So the graph looks like this. So there's our x-axis, and then we have our y-axis. So this is our stress allowable. And over here, this is our 20, 40, 60, 80, 100, 120, 140, 160. And on the x-axis is our L over R ratio. Okay, that's our L over R ratio. So now we have our allowable is at 250. Okay, so this is 100, 200, 300, and all this is megapascal. And we found that our stress critical or the L over R is 88.86. Okay, so I'm going to sketch 88.86. So 88.86, 90 is somewhere around here. Okay, so over here, this is our 88.86 line. Okay, and we know that we have a stress allowable of 250. Okay. Now, this is our L over R. Okay, is equal to 88.86. So this 88.86 is a material based analysis. Okay, why? Because we only look at the Young's modulus and the critical stress. Okay, so at 88.86, what does it mean? Okay, so if the L over R, okay, so on this side, right, on the right hand side, the L over R is greater than 88.86. Okay. On the left hand side, L over R is less than 88.86. This red line I've drawn, if your L over R ratio is greater than 88.86, okay, you have to structure analysis is based on buckling. Okay, i.e., you have to apply the formula where stress critical is equal to pi squared E over L over R squared. If your structure is less then 88.86. Okay, so you are going to apply your stress critical is equal to P divided by A. Okay, so on the left hand side, basically if your L